Get it? Because of coronavirus. Hi, AP Chemistry at home. Welcome to the new classroom. It's a window, but there's whiteboards, so we're gonna learn, I guess. Hat, I know. Sorry, it's been really difficult to find someone to cut hair. So, uh, doing my hair like with the faux hawk thing, I tried. So, I hope you can still take me seriously. Miss you guys. I hope that the quarantine hasn't been too terrible, and that your parents and guardians are entertaining you and having a lot of fun. Before we get started with our new unit, this is a revisit lecture, so that's good news, right? Um, I thought I'd show you a couple things that we've done. But one of the things that my oldest daughter and I have done is we've done draw challenges where I come up with something really stupid for her to try to draw, and then she draws it, and then we go and see if someone else can guess what the challenge was. So uh, I have a few that I really like. So again, look at what she drew and see if you can figure out what it was she was supposed to draw. All right, check out that one. All right, come up with your guess. All right, and this was supposed to be a dummy or a marionette doing science. That's pretty good. That was pretty good. All right. This is Spades, by the way. He lives here, but he coughed the other day, so we have to kill him now, I guess. All right, number two. No, hey, no, 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 no. You go. I was kidding. The challenge was a Native American burying things he shouldn't. And if you see, they're burying directly out of the trash can into the ground. He's awesome. All right, and seriously, I swear this isn't like a magic trick. Go away. And then finally, come up with your guess. What the heck did I tell her to draw? And this is a pumpkin playing a flute, but he's been left in the sun for too long. And she took in the sun pretty literally because he's in the sun. So big AP news. Your exam is now optional if you paid for it. Full refunds. It's an all FRQ test, which again, as I posted in Schoology, I think is good news, and partial credit everywhere. And we're going to do what we planned on doing. I'm still going to go through electrochemistry. You're just not going to receive a test on it. You will be tested over the gas law stuff that we're about to start. But my job isn't just to get you ready for the AP. That's 90% of my job is to help you pass the AP test. But just because they've changed the rules based on coronavirus doesn't mean that when you go to college and you take a chemistry course that you don't want to have ever seen electrochemistry. So we will do some electro lectures, just no tests because it will not be a part of your FRQs. So here's something I know, God, you've wanted to see this for a long time. Oh, look at that. There he is. All right. So go ahead and get your slides out that I'm sure you've already copied. And this is a revisit lecture, so I think that you'll be fine. Actually, you're going to recognize stuff from all three gas laws lectures from pre-AP, so that's great news. As I always like to say, spiral calculator, and do you need a periodic table today? I don't think you need a periodic table today, but hopefully you have access to one for later. So are you ready? All right, I know it's 4.5 minutes. Somebody comment on YouTube that the lecture doesn't actually start till 4 minutes and 30 seconds because I just wasted a bunch of time. So let's go to this slide here. All right. And start talking about gases. So we know that the gas phase compared to the other phases is the least dense particles furthest apart, particles moving with the highest speed, and the most unpredictable. All of the gases are moving around with random motion. When we talk about ideal gases, which will be in the next lecture, we'll talk about the fact that there's no attraction or repulsion between gas particles. All of the motion is truly random. Whereas, you go back to the particle diagrams that we've drawn of solids, and you know exactly where they're expected to be because the structure is so predictable and organized. Whereas our gases aren't. So as we start talking about our gases, I might have a daughter visit. I hope they come and visit, because then they get to be on this video forever. When we start talking about all the different ways that we're going to look at gases, the common items that we'll be talking about is pressure, temperature, volume, because those are the items that when you look at the way a gas is existing in a given setting, if you alter one of those things, it throws off all of the other. The other thing that's on that slide that you're looking at right now is STP, standard temperature and pressure. What's interesting about gases is that the standard temperature is different for gases than it is for other stuff that we've talked about. In the very first unit that we did this school year, when I introduced standard temperature, it was room temperature, which is 25 degrees Celsius. So up until now, you've been used to, when we just talk about a most normal temperature, it being that 25 degrees Celsius. Of course, you have to add 273 to it to get to Kelvin. But gases are different, all right? The STP, the standard for gases, is going to be 0 degrees Celsius, which is 273 Kelvin. So you're going to want to not get that mixed up. You'll also see some basic pressure conversions on that slide. The fact that 1 atmosphere equals 760 millimeters of mercury and 760 torr. That'll be real important because those are real simple conversions that I know that you're able to do, but problems a lot of the time. You'll see that we pretty much want everything in atmospheres, because when we start, not today, but in the next lecture, because our values, a constant value, is going to be measured in atmospheres. There's other R's we could use, but we're not going to. It'll be easier just to use a singular value for R and then just make everything be atmosphere. So that's a good habit to get into, but you'll see today that it's not absolutely necessary. All of our gas laws, all of our equations that we'll be learning, you are required to be in Kelvin. So make sure that anytime degrees Celsius shows up, which it normally will, because all of our measuring devices for the real world happen in degrees Celsius or degrees Fahrenheit, but we won't say that in here because we're not, stupid. This is cat number 2. I mean, did you this is Denarius. Come here. No, we love each other. Say hi. Oh, you're a good kitty. Okay, shut up. Anyway, I was saying stuff. Everything must be in Kelvin. So one of the things you'll notice that I definitely don't want to trick you, though, is that if temperature is something you're solving for and all of your answer choices are in Celsius, well, keep in mind that in that particular instance, you would need to convert a given Celsius to Kelvin, input into the equation. It's going to spit out Kelvin because these equations can only have Kelvin put in for temperature and can only give out Kelvin for temperature. And then you'd have to convert back to Celsius, which is just subtracting 273 in order to get there. So there's some of our basic intro stuff. So let's get into the combined gas law. So this is the slide that we're on now. It's interesting, the combined gas law won't be on your AP sheet, but studying it and being good at it is going to help you both in conceptual and mathematical questions, just understanding the connection between pressure, volume, and temperature. So there's your equation, P1 V1 over T1 equals P2 V2 over T2. You've used this equation in your science life before. But it's a combination of 3 different laws. And there's actually a 4th law that you see in there sometimes, which is Avogadro's law, which deals with moles. I'm going to look at that from a different angle, but you could have N1 and N2 on the bottom with temperature. But anyhow, this is a connection or a combination of Boyle's, Charles, and Lussig's law. You do need to know which scientist is in charge of which association. So when I say Boyle's law, your brain should immediately go pressure and volume. All right, and I go like this because it's the only connection here in the way that I've written the combined gas law to have an inverse relationship. If you remember, and I would demo the pre-AP stuff like I did last year when we introduced the combined gas law. I'm at home, so I don't have that stuff. But Boyle's Law was the potato gun. All right. If you remember, I took a hollow tube and I stabbed a potato on one end, and then I stabbed a potato on the other end so that there was a potato wedge on each side of the hollow tube. And then using a plunger, I pushed one towards the other. And as I did that, the gas that was trapped in between the two potato wedges, the volume went way down. It had less space to exist. So as I pushed one towards the other, the amount of volume available went down. And according to Boyle, that makes the pressure go up. So what eventually happened as I kept pushing, you had this explosion of potato, and boom, we were eating French fries. Charles is our first of the direct laws, which is going to be our combination of temperature and volume. And they're direct. All right. It states that if the temperature goes up, the volume goes up. The demo that I usually do for this is a balloon, or some of y'all have experienced the instance where if you leave a balloon in a car on a hot day, the balloon can pop. Why does it pop? Well, it's because once the gases inside that balloon started to heat up, they tried to take up more space, and usually the balloon won't allow that to happen. So what happens? Boom. Um, the demo I do is actually a lie. For those of y'all that remember last year, I have a blown up balloon, and I would tell you that I'm going to drop it into a bucket of ice, and I dropped it and the balloon would disappear. But I had another bucket next to it with a really little balloon already in there. People in the back of the room couldn't see it, but when it was on ice for 10 seconds, I would reach into the other bucket and pull out a much smaller balloon and be like, oh my God, it shrunk. And it was stupid, but sometimes it helps you remember. But anyways, in that case, the temperature went down, so the volume went down since it's a direct relationship. And then Lussig's law is temperature and volume. Again, a direct relationship. What one does, the other one will also do. If I had had the foresight to make it to campus and steal some of this stuff, we have the hand boiler where, and you could actually Google hand boiler and you can watch it and remember that I showed you last year, but it was that glass contraption where when I just held the bottom of it, the temperature from my hand would go into would conduct into the glass tube, and it would make the oh, sorry, Lussig's temperature and pressure. Did I say volume now? I feel like I repeat. Oh, because it's printed badly on the slide. Anyways, typo on the slide. This is fun. Yeah, Lussig is dealing with temperature and pressure. Anyhow, it makes the pressure inside that glass tube go wild, and the water would look like it was boiling just by my hand grabbing it. Sorry about that. Anyway, so that's the conceptual look at the combined gas law. Where you're going to need to, again, be able to know which scientist is associated with which association, and then, of course, know whether the properties are inversely or directly connected. So let's practice. Now, hey, these boards they wobble a little bit, so when one falls, and you might think it's hilarious, I'm sorry. But anyway, so if you look on the next slide, you'll see that there are two combined gas law problems for us to work through. I don't think they'll cause us any trouble, but we definitely want to be able to do this. 545 milliliter sample of nitrogen gas, initially at negative 220 degrees Celsius, is heated to 100 degrees Celsius. Calculate the volume, assuming the pressure does not change. So one of the things that's real important about using the combined gas law is a lot of times you'll run into a problem that doesn't use all the variables. When that happens, you just ignore the variables that you're not messing with, because the problem, in this case, it distinctly says it, but the problem is assuming that dimension of the gas situation is staying constant. So anyway, if I do this in my simplest way of solving and I just extract the numbers that I see, all right, we'll start with 545 mils, all right. Is that showing up? Yeah. All right, we've got negative 220 degrees Celsius, all right, and then followed by 100 degrees Celsius. All right, and then I'm just going to put a little question mark down there because now it's going to want me to find something. So if I identify what these units are telling me, and by the way, guys, milliliters is fine here for the combined gas law. It's just whatever units go in will be the units that come out. You'll see when we do the ideal gas law that very particular units have to go in because of R. But for here, milliliters is fine. It's just if we put milliliters in, milliliters is going to come out. What's not fine is degrees Celsius. Degrees Celsius is never okay. All temperature readings must be in Kelvin. So you'll see that as I identify these as my V1 and my T1 and my T2, and I want to know V2, then I can easily plug into the equation, but not with Celsius. So what we want to do here is, so V1 over T1, if you look at the equation, is going to end up being 545, and that'll be over. Now remember, not negative 220, it's actually going to be 53 Kelvin, all right? I added 273 to the negative 220. That 273, you don't have to memorize, that is on your AP sheet on how to get from degrees Celsius to Kelvin. Is going to equal V2 over T2. I like to still use X for when we're doing this basic algebra. You can put V2 there or whatever, but that's going to be over 373. Again, that's a conversion of your degrees Celsius. And when I finish working it out, I'm going to get 3,800 mils. Now, yes, I went to 2 sig figs. You'll notice that in the problem, the way it's printed on your slide, it gave one of the temperatures with 1 sig fig. That's always a mistake, and I suck. I'm sorry, but AP will never give you a 1 sig fig problem, so I added a decimal there. But anyway, 3,800 mils, and what you'll notice is that it absolutely matches the law that we say, because volume and temperature are directly related. And what you'll notice is that the temperature is going up. Therefore, we would immediately assume that the volume is going to go up, and we prove that concept true using this more specific math. I suggest before I work out the next one that you pause the video and see if you can work out the next problem and get to an answer. Your call, but I'm just going to go ahead and work out the next problem dealing with helium. All right, I'm going to go ahead and pull out the values of that next problem. What I see is negative 33 degrees Celsius. I see 1.23 atmospheres. I see 2.34 liters, followed by 54.5 degrees Celsius. And then 1,026 millimeters of mercury. All right, add a little question mark because I know they'll be looking for something. All right, so just going through your basic labels in your brain, degrees Celsius is going to be my temperatures, atmospheres is units of pressure, and then liters is going to be units of volume. So down here, it looks like I'm missing a volume, which could immediately let me know that that is what it's looking for. So it wants to calculate the new volume. Um, So we can start, this uses all the variables from the combined gas law, so we can go the P1, V1 over T1 and get everything plugged in. Of course, my degrees Celsius is no good. So as I start with my P1 is going to be my 1.23. All right. And then my V1 is what's actually missing here. And that'll be over my T1, where my negative 33 plus 273 is going to be 240. All right. And then going to the other side of the equation for my P2 is 1.35. Oh, I'm sorry. Let's say I don't see that number up here. Hey, look what happened. The atmospheres and millimeters of mercury are listed in different pressure units, which of course is not okay. And they need to either both be atmospheres or both be millimeters of mercury, but it's a simple conversion to get there. So if you flip back to the first slide of this lecture, you'll see the conversion factors for getting atmospheres and millimeters of mercury the same. So I don't want the 1026 millimeters of mercury. We want to convert that to atmospheres, which is ultimately going to be 1026 divided by 760 if you were to put it into a one-step dimensional analysis on that conversion. And then upon converting that, you'll end up with 1.35 atmospheres. All right, so there's P2, all right. My V2 is the 2.34. And then that is going over my T2 of 327.5, which is a conversion of degrees Celsius. Yes, question in the back? Oh, there's nobody here. Okay. So, and then solve, and we'll see if we end up with a common answer. And I get 1.88 liters.
I don't know where to write
The other law that we're going to look at today is another one that you'll recognize, and it's Dalton's law. All right. This equation is given to you on the sheet, but it's such a simple equation that very rarely do they ever ask a question that's just directly using it. It just looks at the fact that if you want to know the total pressure in a system, then you would have to sum together all of the partial pressures of each gas that makes up the system. So, I mean, very simply put, if I were to make the assumption that in this wonderful kitchen, the gases that make it up are oxygen, nitrogen, and carbon dioxide, then if I wanted to know the total pressure of gases, the total pressure in the kitchen based off gases, I would need to add up, well, the total pressure the oxygen is giving, plus the total pressure the nitrogen is giving, plus the total pressure that the carbon dioxide is giving, and add up the partial pressures, and it would give you the total pressure. You'll notice there's an ellipses inside the equation. That's just because you could be dealing with a system made up of 2 gases, or you could be dealing with a system made up of 200 gases. But either way, you would just need to add them together. So the idea is that simple. However, what it's most commonly applied to is our collection of gas experimentally. That lab setup that you see there is the lab that we would have, this right here, we would have done this. I've got the write-up for it, but I don't know if that's happening. But anyhow, this is called collecting gases over water. The issue with this, though, and the reason there's another equation there, is that this is the best way to collect a pure sample of water. For example, if we had a lighter that had butane in it, all right, which is going to be the flammable gas that makes the lighter work. What we could do is put an upside down graduated cylinder, an inverted graduated cylinder into water, fill it with water, all right, so that now it's upside down, and as long as the mouth of the graduated cylinder doesn't go above the surface of the water will stay suspended in it. But then if I put my hand under the water and I just hold down the button of that lighter, butane bubbles will start to go up, and as that happens, the water level that's stuck in that upside down graduated cylinder will drop as it fills with pure butane. And what we can do is run calculations to figure out the pressure that's being exerted inside. We can also do cool stuff like figure out the molar mass of the butane. But the issue is that the water itself is distributing or adding pressure to the total system. Not a lot, but when you go through this collected over water process, the water itself is adding water pressure to the pressure of the other gas. And that water vapor pressure is something that we have to account for. So what this says for collecting gas over water is that if I want the total pressure of the system, well, then I have to add the total pressure of the gas I've collected plus the pressure of the water. Now, how do we find the pressure of the water? There's a chart for that. You don't have to memorize this, and it'll be provided to you for any test questions that require water vapor pressure. I would have given you a sheet today, but I don't get to see your beautiful face, except for the one of you that's not beautiful. You know who I'm talking about. So what you need to do for Schoology is just go look it up. They're constant values. Just type in water vapor pressure chart, and it will come up with all the different pressures that water distributes using this process based on the temperature of the water, and that's how we know what it's going to do. So let's take a look at a problem. All right, so here we are. Man, these lectures go a little bit faster when I don't have a bunch of children's yelling at me and raising their hands. All right, so if I take a look at this problem, it says that we're going to be collecting oxygen over water, and then it gives us some stuff. So if we just think a moment about the equation, which again, just so we can see it, all right, it's the total pressure is going to be the pressure of, well, let's just do the O2 because of the way this problem is. Excuse me, the pressure of the O2 plus the water pressure. All right, so that's ultimately what we're dealing with here. So now we just got to figure out what's what. Now, if you look at the problem, it gives you a total pressure of 765. All right, so we've got 765 millimeters of mercury, or is it torr? All right, yeah, millimeters of mercury. All right, so we know that this is what it equals. All right, and it wants to know the pressure of the oxygen. So that's what we're solving for. The other information it gives us is the temperature of the water. And like I said, you'll need to go use your Google machine and look up, okay, well, what is the pressure of water if the water is 24 degrees Celsius, which is what it is in this problem. And what you'll find out is that the water pressure here, based on that temperature, is 22.4. And suddenly this becomes a very simple problem in regards to solving for x. I get 743 millimeters of mercury. All right, and that is the one more problem. All my markers are that way. say hi to the people. Come here. Come here. Jarvis. Wait, are you wet? A little bit. I have a dog, but I don't know if she's gonna go say hi. Oh, say hello. Oh, there they are. There they are. Say hello to everybody. There's a good girl. Oh, you smell. You don't smell nice. You don't smell nice. Okay. All right, let's take a look at this last problem. Make sure you don't think it's tricky. All right, so a couple things going on because this is going to make us use Dalton's law and collecting gas over water first, and then the information we get from that, it then wants us to change the system, which means the combined gas law will help us out in order to get a final answer. So the very first thing that I notice is that it does give me a total pressure again. So this time I've got a total pressure of 738 torr, all right? And that system right there is, again, if I want to find what type of gas, oh, it just says of gas. So if I want to know what the pressure is of the gas in this system, all right, so I've got the pressure of the gas plus the pressure of water. The temperature that it gives this time is 28 degrees Celsius, so we go and look it up, all right, and we'll see that this value right here, all right, is actually 28.3. All right, so now we can solve for 28.3 plus what is 738, and we'll see that it's 710 torr. So this value right here is going to be 710 torr. All right. But that's not all it wants to know. It wants to know, okay, well, if this is the pressure, all right, and based on this gas sample that we've collected, what would it be, or rather, what would the volume be if the conditions were STP? All right, not Stone Temple Pilots. Y'all aren't old enough to get that reference. But anyway, so now we can plug and chug into the combined gas law. All right, starting with my pressure. All right, well, my pressure that we just found is 710. That's P1. All right, we'll go to our V1, which is given in the problem. All right, the starting volume was 235 mils. 235 mils. All right, P1, V1. And then my starting temperature was 28 degrees Celsius. Degrees Celsius is no good. That's going to be 301 Kelvin. All right, I'm sorry that I guess I could just go straight across. I'm just stupid. All right, so we're going to go across boards now. All right, and set that equal to P2, V2 over T2. All right, but what are those values? Well, it's at STP. So if it's going to be at STP, then I know what those values are always equal. So my P2 needs to be the don't do that. The cat just licked the Lysol. Told you I was going to kill a cat before this lecture was over. The issue with our STP is that it's expressed in atmospheres. If you go back and look at 0 degrees Celsius in 1 atmosphere, I've already committed to this idea of using torr here. So I could change that 710 to atmospheres and then use 1 over here, but whatever. I'm just going to use STP in torr, which is 760. All right, because 1 atmosphere equals 760 torr. So there's my P2. My V2 is what we are trying to find. And then over my T2, all right, which is my standard temperature, 0 degrees Celsius, 273 Kelvin. Now I've used Dalton, I've used combined, and we are able to report an answer of, pause it and work it out. I get 199 milliliters. So for those of y'all that are not home with COVID, not that you have it, but you're not stuck at home like we are, because this is a new school year and I'm probably not going to remake this video. I'm glad you got to get a glimpse of the kitchen. The next two videos, unless something changes and I make it up to Madison, will be in the same format. So if it's much worse than my other videos, I'm sorry. But we're all doing our best, right? Hey, there's a discussion item available in Schoology where instead of you, if you want to send me private messages, that's fine. But if you jotted down questions or whatever, or things you didn't understand from this lecture, post your questions there, because that would create a situation where it might have been the type of thing that somebody would raise their hand during the lecture and ask, which usually benefits multiple students because they didn't know they had your question, but now you've clarified something for them. So if you get into the habit of posting, not necessarily Schoology question. If you have a question about a Schoology question from an assignment, then private message. But if you have a question about the lecture, then go to that discussion thread, type it into there, and I'll answer it, and we can have a chemistry conversation. Miss you guys. Stay safe.